All right. Wow, in-person conference. This feels good. Thank you so much, Lauren and Bernd, for organizing this, for inviting us all to come and gather, and as both of you always do, to help people talk to each other who might not realize that we need to talk to each other. So that's really great. Right, so the title of my talk is Nonlinear Spaces from Linear Spaces. And I might add 4 linear spaces also. Okay. Let me begin by saying that all the speakers received a wonderful email from the organizers saying, make sure that your talks are actually accessible. So instead of trying to talk about like the hottest new thing, let's actually talk about, the stories that we think about in the kind of most honest and clear way that we can. And so that's my goal for this talk. And so in that spirit, any questions that you have, please feel free to ask them. Okay, so when I was invited to speak, I kind of knew what the general thing was that I wanted to talk about. But if you've seen me talk about this kind of thing, I wanted to tell. I want to talk about the work of many people, and to some extent, some of the work that I've done. So let me say that the work that I've done is with Carly Kleidens, a paper from 2006, with Adam Booker, in 2013, and with Graham Denham and Juni Ha in 22. All of these papers are on the archive. I think they are each. Okay. These are the only papers with those authors, and here we have 2 papers with Graham Denham. So I'm going to talk about the first one. The second one is related. This is in Journal of Combinatorial Theory, Journal of Algebra Combinatorics, and actually this just went up on Journal of American Math Society a couple of days ago. So you can find them there. Just as a kind of a motivation, I want to start by just writing a list of numbers and ask you what you notice about them. Okay? So while I write them, you can stare at them and see what you notice. So what do you notice? And if you have a guess as to where I got these numbers, you can talk to your neighbor about where you think they are coming from. And also, what do you notice about them? Let me ask the students. Do you notice anything about the sequence of numbers, or do you have a guess as to where I got it from? Any observations? Yeah?
It's unimotal.
What does that word mean?
Like it goes up and goes down.
So these numbers go up and then down, right? Okay. Does anybody have a guess as to where I got these numbers?
Oh yeah, yes.
No, that's not where I got them. Any other guesses?
Temperature during the day.
This is a hint is how many numbers are there? There's 12 numbers. This is the average temperature in Boston, Massachusetts, January, February, March, and so on. Okay. These numbers are unimodal. Okay. Now, maybe many of you grew up in places where this was very familiar to you, but I'm from the tropics, and where I come from, this sequence, so I looked it up for Bogota, where I come from, and the sequence is 55, 56, 55. That's what the sequence looks like in Bogota. And so one thing that happens is that actually when you are from the tropics, you don't talk a lot about seasons and you don't really not really understand them very well. And for a long time, I was very confused, actually, as to like, okay, I get it. I've heard of seasons, but like, why? And it's something that, because it's not relevant to ourselves in Colombia, like we just didn't really, I'm sure we learned it at some point, but nobody paid attention because it was like something that happened somewhere else. But the reason I'm saying this is because I want you to just pause for a moment and think historically, like, okay, surely people noticed temperatures go up and down throughout millennia. But think about what it takes to explain that. What do you need to know to understand seasons? So you need to understand that the Earth is round. You need to understand that it orbits around the sun. And this is the part that I find really confusing. You also need to understand that it kind of orbits not like this, but at an angle, right? So it's kind of going like this. And that, as I understand it, is what causes seasons. The point in telling you all of this is that this is a very kind of elementary observation you can make. And it might not even be so important, or maybe it is important to you why the numbers go up and down. But in order to explain a phenomenon like this, you really have to make a lot of connections and a lot of understanding of things that just are very far from where you are. Okay? And so what I want to tell you today is some mathematical story that is kind of parallel to this. So it starts like this. So let me begin with three equivalent constructions that I can make. The first one, let me start with the second one. So this is a matrix, okay? And I want to think of the columns of the matrix as being vectors, which I drew over here, okay? So this is the first one. This is the second one. This is the third one. Okay, so those are the three unit vectors. And then 1, 1. So this is the fourth one. And 1, 3. So this is the fifth one. Okay. So this is what I might call a vector configuration. Something that we like to do is regard it as a hyperplane arrangement instead. So every vector has a hyperplane orthogonal to it. And so the hyperplane orthogonal to 1 is this plane, right? Which I'm just going to draw like this, okay? And so this is going to be hyperplane 1. And I want you to think that it's a whole plane, but everything passes through the origin. And so I just want to draw the line so that it's a little bit easier to see. 2, so that's going to be over here. 3, the perpendicular to this is over here. Okay, and they actually keep going, right? And then 4 and 5 are a little bit trickier to draw, but one thing that I can do is realize, okay, because 4, 1, and 2 are on the same plane, that means that those 3 planes should pass through a shared line, and I guess that means that 4 passes through here, so it's going to be something like this. And 5 is 1 and 3, so 1, 3, and 5 should pass through here. And so that's my picture of the hyperplane arrangement of 5 planes in 3 space. And I should say, like, I spend a lot of time looking at pictures like this, but they're confusing at first. So does anybody have any questions about what I'm drawing here? It's going to be important. So again, each line represents the plane passing through that line and the origin, okay? Okay, so now here's what I'm going to do. So I'm going to start with an arrangement of n hyperplanes in CR, okay? And I want to tell 3 stories. So the first thing I'm going to do is that I'm going to see how those hyperplanes intersect. And I'm going to let Wi be the number of intersections of dimension r minus I. Okay? So let's see how that goes here. So what are the intersections of of these 5 planes. So first of all, there's just like the 5 planes, so the intersection of one at a time. So 5 of the planes. And those are the things of dimension 2. Okay? What about the lines? Well, the lines where they intersect are going to be the points in this picture, right? So there's and then I realize that I'm actually missing some because these ones intersect over here. These ones intersect over here. And so I have 1, 2, 3, 4, 5, 6. Okay? So those are the 6 lines. Okay? Now, when I intersect so the intersections of dimension 0, well, that's just the origin, right? So the origin is the only thing of intersection 0, and then of intersection 3, of dimension 3, I can consider like the empty intersection of no hyperplanes, and so that's the sequence. Okay? And many, many years ago, it was observed that no matter what you start with, what matrix you start with, what hyperplane arrangement you start with, these numbers also have this property that they're unimodal. Okay? And so let me state a conjecture / theorem. So, and I think I'm going to so part of this is theorem, part of this is conjecture, but this field moves very quickly these days, and so if the conjecture has been proved, somebody please tell me. But the theorem is that these numbers go up until the middle, okay? And I believe it's a conjecture that they then go down till the end. Does anybody know if this has been proved? This has not been proved, right? So the second half is still conjectural. Okay, so even this we don't understand yet. And the other thing that happens is that this is a top-heavy sequence, meaning that the ith entry is less than or equal to the r minus ith entry. Okay? So that's part theorem, part conjecture.
Is the top-heaviness theorem or conjecture? Sorry.
I'm sorry?
Was the top-heaviness a theorem or a conjecture?
So I don't know if it's hard to see, but the yellow part is what's conjectural. And the things that I wrote in white are theorems. So that's the first story, okay? And so I want to say a little bit about why we know that this is true. But before I do that, let me tell you a different but related story. So, so what I'm going to do is that I'm going to pretend now that my arrangement is not over the complex numbers, but over a finite field. So I'm going to take the same equations and regard them as equations over a finite field. I can't always do this, but pretty much any arrangement that we're interested in has integer coordinates. And if it has integer coordinates, then you can pretend that is an arrangement over a finite field, okay? And now what I'm going to do is that I'm going to count how many points are in my vector space that's over a finite field. So far there's q to the r points, right? Because this is a finite field to the r. But I remove the hyperplanes of the arrangement. Okay? So let's do it here. Okay, so and this is fun to do. So I need to choose a point. Now thinking that this is fq to the 3. So a point is a triple. And that point should be off of these hyperplanes. So the point S1, S2, S3 should be off of these hyperplanes, meaning that it should not satisfy any of those equations. Okay? So then, how many options do I have for S1? Well, S1 cannot be 0. So I have q options except for S1 cannot be 0. What about S2? Well, S2 cannot be 0, and S2 cannot be negative S1. So not 0, not negative S1. And these two numbers are different because S1 is not 0. So two things disappear. And then for the last one, S3 cannot be 0, and it also cannot be negative S1. So I get this. Okay. And if I multiply this out, I get this. Okay. And so the first thing I notice is that this is a polynomial. And then the second thing I notice, given that we're talking about this, is that the numbers also go up and down. So, theorem. This is a polynomial in Q. I have to put a little bit of a disclaimer, which is that there might be some number theory problems at small primes. So you need to choose Q to be p to the alpha for p large enough. And again, for the arrangement I care about, large enough usually means it's not 2. I mean, it's like, this is not really a big restriction. So it's a polynomial in Q whose signs alternate plus minus, plus minus, plus minus, and whose coefficients, when I remove the signs, are also unimodal, meaning they go up and then down. And an even stronger statement is that they are log concave, meaning that their logarithms form a concave sequence. So each number squared is greater than or equal to the product to its left and to its right. And that implies unimodality. Okay, so that's a theorem. Which we see here. Okay. And then the last statement that okay, but before I say the last statement, does anybody have any questions about what I'm saying so far? Okay. The last thing I'm going to do is simply say that if I do this at q plus 1, then you can see that it's going to be kind of a polynomial with smaller coefficients. And the theorem is that this one also satisfies this properties. Same for okay. And when I say it like this, I feel like it's like, okay, so q plus 1, why is that? Should I try q plus 2 then? Well, q plus 2 doesn't work, first of all. But this is the shortest way that I can get to the story, but there's a different way of saying this, which explains that this is an f vector of some simplified complex. This is the h vector, and so there are reasons why we care about each one of these specifically. These are not plugging in at random places. One way that you might think about the difference between these two statements is, as I'm telling this story in this way, which I've never tried before, is that it's a little bit like this. It's a little bit like temperatures. That it's the same. Okay, so if you want to explain these things, the explanation is kind of common. You need to find connections to something else that's probably outside of the world of linearity that you're in. And if you look at it from a certain angle, like Boston, it might be more obvious what's happening. And if you look at it from Bogota, well, it's still kind of unimodal, but somehow you're going to have to work harder to understand it. So it's a slightly parallel story, and I'll say more about what that means. Okay, but this is the summary of the 3 statements that I want to talk about today, with the kind of contextualization that the reason that I care about these statements is, well, first of all, because it's just fun to explain a phenomenon like this. But usually, combinatorics has been very interested in phenomena like this. Not particularly because we are so, it's not so important to us that numbers go up and then down. Like we're not trying to plan the farming of our of our food, but we just know from experience that these questions, when like if we can't figure them out that afternoon, usually we're gonna spend some years on it, and we're gonna find connections to algebraic geometry, to representation theory of SL2, to Hodge theory. We kind of know by now that this leads to deeper connections, and that's why we're interested in. Okay. So that's the first part of the story. Let me just write it down. So the conjectures are from the 70s and 80s. All of these conjectures, and they became theorems in the 10s and 20s, meaning like right now. And the point that I'm trying to make is that to go from here to here, to go from conjecture to theorem and these things, we basically needed to really understand something fundamentally new. And so this is where we need connections with algebraic geometry, with Hodge theory, with representations of SL2. I'm repeating myself, but maybe because this is a workshop on linear algebra, nonlinear algebra and combinatorics, I think one thing that preparing this talk helped me understand is that this is very much something where we have a phenomenon that's linear, but like we don't really have a linear explanation. We actually need to go into the realm of algebraic geometry and say, okay, we're going to actually think of these not as linear algebra, but as nonlinear algebra, and use tools from there, and actually use some constructions here. So I want to show you that actually nonlinear constructions play a very important role here. Okay. One part of the story, which is a part of the story that I love very much, and anybody who knows me, my mathematics knows that I like very much a parallel story, a more general story, which is that this is also true for matroids. Okay, so for any matroid, so whenever I have a configuration like this, if I pay attention to the combinatorics of which hyperplanes intersect in which dimension, that's what I call the matroid of this configuration. So any configuration like this leads to a matroid, but matroids are a much more general thing, and matroids are much better behaved than these things in some particular ways. And you can formulate everything combinatorially, and you can do all of this for matroids, and then in some sense, you now have to, so most of the ways that we know how to do this go through this technique of tropicalization, where like now you take nonlinear things and you end up doing like piecewise linearity. So this is like piecewise linearity and combinatorics. And if anybody wants to talk about this Bergman fan, or this conormal fan, or this augmented Bergman fan, there's a beautiful story that now that there's so many talks online, if you Google enough, you'll find talks where I talk about this part of the story. But maybe one thing that I would say is that this is like the combinatorial tropical analog of basically thinking of these matroids non-linearly. So now we're doing like non-linear tropical geometry to get to linear tropical geometry. Okay, so I think that's kind of the overview. And now let's get to how we actually do this. Any questions while I erase the board?
Yeah, I have a question.
Yep.
So the example you wrote was a complexification of a real hyperplane arrangement, but presumably this also works for generic complex hyperplane arrangements?
Yeah. So this works for any. And I started with complex arrangement, but this could be over any field. It doesn't even need to be complex. And the point of the story of matrix is that you don't even have to be able to realize it as an arrangement. But yeah, this is perfectly general. But the techniques actually sometimes have to be adapted, so that is part of the story. Okay, so maybe the second part then will be talking about like from nonlinearity. So and I might say like when linearity and combinatorics are not enough, you go to these nonlinear spaces. So what I'm going to do is that for each one of these three stories, I'm going to construct a geometric space that is not really linear, and that is going to hold the key to understanding these theorems. Okay, so I'm going to, if there's time, my plan for the rest of the talk is just to show you three constructions. So we'll start with B. Okay. And this begins with work of De Concini and Procesi, and the explanation that I'm going to give is due to Ha and Katz. So what I'm going to do is that I'm going to consider a map from Cn to two copies of Cn, where I take a vector here, and I go to V and V inverse. What do I mean here? I just mean taking the coordinate-wise inverses of the. So these are like the n coordinates and their inverses. Okay. I can almost do this, but I should make sure that I'm not dividing by 0. So this is defined on the torus C star to the n, meaning that I shouldn't have 0 coordinates. But so if it's defined here, that means that I can define it on the intersection of this vector space with C star to the n. So what vector space am I talking about here? My vector space is going to be the row space of my matrix. Okay, so I take this. It's some vector space in C5, and I just remove its intersection with the coordinate planes. And then I get this map, and this I'm going to call M, which is the arrangement complement. Okay, so I think here I should say a little bit about why I'm calling this the arrangement complement. And the reason is this, that if so my matrix A maps C5 to C3 by multiplication, right? One thing that is not difficult to see is that this subspace V maps isomorphically. So I can think of this V as a copy of C3 inside C5. But the nice thing about this is that the coordinate hyperplanes here are going to map precisely to these 5 hyperplanes. Okay, so here I have 5 coordinate hyperplanes in C5, but when I do this map, I get 5 hyperplanes in C3, and they're exactly my arrangement. Okay, and so that means that if I take this thing that I put here, V minus the coordinate hyperplanes over here, it basically is the same thing as C3 minus my arrangement. Okay, so it basically identifies these two things, and so this is what I'm calling M. Okay, so being a little bit sloppy here, but I'm going to call both of these things M. Okay, and so that's why I call this the arrangement complement. Okay, and so what was I saying? I was saying I consider this map. Okay, this map is not defined on all of Cm, but it is defined on M. And so what I'm going to do is consider the image. So I don't know. Let's call this like phi. So I'm going to consider phi of my arrangement complement, which is basically like, I mean, I'm thinking phi of v. That's really what I'm thinking, but I just have to remember I can't plug in all of v. So phi of n. Okay, so that's that's something over here, and then I take this Zariski closure, and this is going to give me some variety. Okay. This is the graph of the Cremona transformation, if you like these words, and you can see that actually this doesn't really depend on scaling. So I can, instead of doing this over Cn, I can do it projectively, and I want to do that. So I get some variety in a product of two projective spaces. Okay, and again, one important point is that this is like, it's kind of like a model of my vector space, but it's not linear anymore. Okay, and the thing is that like, okay, once you have a variety, a subvariety of a variety, there's this whole technology of Chow rings that helps you kind of understand how this goes. And let me say it very roughly that just like in a topological space, homology theory is supposed to detect holes. In an algebraic variety, Chow cohomology is supposed to detect subvarieties, and modulo some equivalence, right? So like just like in homology, you have to identify many things so that you can see that a ball only has one hole. But here you have to identify many subvarieties, and you want to say what are really the honestly different subvarieties. Okay. And so this thing has a very nice Chow ring, which again you can think of as the cohomology. The Chow ring of this variety. This thing ends up being given by the following thing. So first of all, I should tell you that what classes in this Chow ring look like. They look like products of a PA and a PB. And what you get in this particular, so any class in the Chow ring is going to be a formal sum of products of a PA and a PB. This particular one looks like this. With some coefficients, and the coefficients here, mu I, are exactly the coefficients that I want to prove are unimodal. Coefficients. Actually, that's not exactly true. It's pretty much true. It's the coefficients of this polynomial divided by q minus 1. And the reason that this is a useful thing to do, first of all, I think it's a beautiful result. So it's giving a geometric interpretation of these numbers. But then basically you have the technology of algebraic geometry that tells you in this situation these things are unimodal, they are log concave, and you're done. Okay, so this implies unimodality and log concavity. Okay, and this is more or less what Juni Ho did in his PhD thesis that kind of got a lot of this stuff going. So the exposition that I'm giving is closer to Ho and Katz, but this is basically the general procedure to try to understand these conjectures. Okay, so this is the strategy we're after. And I should say that this is where you end up using some results by Hodge, Tessier, and Khovansky. Okay. Meaning to get from here, I mean, to the fact that under sufficiently nice hypotheses, coefficients are always log concave for whatever subvariety you put here. So this is kind of the algebraic geometry package, and this is where a lot of the fun for people like me is to basically take a variety that is not linear, but it's like close enough to linear that you can really understand its combinatorial structure, and you can maybe decompose it into pieces, or you can do some kind of thing to really understand its cohomology class. Okay. And so that's how this is proved, at least in the realizable case. So tell me if you have any questions while I erase the board now. Okay, so let's talk about how you can prove C then. So to prove C, I'm going to need another variety that is somewhat similar to this one, and this is a variety that as far as I understand, was first studied by Barchenko when he was studying critical points of the KZ equation. This also appears prominently in work of Bernd, Strumfels with Catanese, Hostin, and Ketan, computing maximum likelihood degrees. This is also related to the theory of conormal varieties that is explained, for example, in the Gelfand-Kapranov and Zelevinsky book. And again, I promise to be as elementary as I can be, so let me try to do that. So what I'm going to do is the following. I'm going to say that for any lambda in Cn, I'm going to consider a function there's like one tiny piece of fancy chalk here, and I don't know where it went. Oh, here we go. Okay, so the function I'm going to consider is a function from CR.
Special delivery from Chris.
Oh, thank you. So I'm going to map S1 to SR to okay, I'm realizing that I think I have a slight conflict of notation here, but basically the F1, oh no, it's not a conflict. So F1 up to Fn are basically these linear forms. So this is F1, F2, F3, F4, and F5. So those are the linear forms defining my hyperplanes. And now I want to consider this function, okay? Now I have to say I'm not somebody who's used to raising things to complex powers, so I have to be like, okay, how does this go again? So complex powers, you get multi-valued functions, and you have to be very careful. Okay, where are zeros? Where are their poles? Okay, so this is multi-valued. But you're going to be okay as long as you stay off of the zeros and poles. Where are the zeros and poles? Where F1 is 0, F2 is 0, Fn is 0. That's precisely the arrangement. So zeros and poles are precisely at the arrangement. So this function is holomorphic in the complement. Okay, so that's where I want to consider it. And now what I would like to do is find the critical points of this function, and there's several reasons to do this. And I bet you explained this beautifully yesterday, Bernd, and I missed it because I couldn't go to your talk. But if you went to the talk yesterday, probably this was the motivation. One of the motivations to do this was explained. But so the goal is to basically study the critical points of this thing, and not just do it for a particular lambda, but for all lambdas at once. Okay, so I want to collect the critical points of phi lambda for all lambdas at once. Okay, so that's my goal, and I'm going to collect them in an object that I am going to use this letter for. Okay. Okay. So how do I do this? So I need to set the derivative to 0, and because this is all these exponentials, let me take the logarithm. And let me take derivatives. So what I get is this. And I always find it useful to do things in an example, so let me actually carry this out in this example. So in my example, what does this look like? These f1s up to f5s are over there, so I can actually write them down explicitly. So I get lambda 1 times ds1 over s1, lambda 2 ds2 over s2, lambda 3 ds3 over s3, lambda 4 s4 is, now I want f4, which is this. And for this one I get this. And this should be 0. Okay. And for that to be 0, I can basically look at the coefficient of each of the d as i's. And I'm going to get, because I have a ds1, a ds2, and a ds3, I'm going to get 3 equations. So for ds1, the equation that I get is lambda 1 over s1 plus lambda 4 over s1 plus s2 plus lambda 5 over s1 plus s3 equals 0. For ds2, what I get is lambda 2 over s2 plus lambda 4. Please don't let me make any mistakes. This is a place where it's easy to make mistakes. For ds3, I get lambda 3 over s3 plus lambda 5 over s1 plus s3 equals 0. Okay. So these are my 3 conditions that need to be satisfied to get a critical point. Now let me invite you to look at these and compare them to the matrix to the right. It's kind of nice that they landed right there. So do you see how this is related to this? So if you look at this, and you kind of, I might call this S4, I might call this S5. And then you see that these are all linear equations in lambda I over Si. And if you look at what they look like, they're basically 1 plus 4 plus 5 equals 0. and that's this row of this matrix. 2 plus 4 equals 0, and 3 plus 5 equals 0. And so you may think, oh, we got our vector space back. But you realize actually it's not really that vector space that we're getting because the vector space here has some other set of equations, right? So we don't want the row space of this, we want the null space of this. And so for that reason, I need to consider the dual vector space, the dual configuration. And so let me consider that vector space given by those equations. That I get there. Okay, and this is the null space of A. And this has its own vector configuration associated to it that I can get by putting these things what am I doing here? Let me write this down and then I'll understand what I write down. Right, so what I'm doing is choosing a basis of this, and one way that I can choose that basis is just by using these equations. So x4 equals x plus 1 plus x2, so I get minus x1 minus x2 plus x4, and then minus x1 minus x3 plus x5. So basically I'm now using that this is the row space of some other, the null space of that. So I get another vector configuration, and I get another hyperplane arrangement. Which is given by the columns of this thing. Okay? And this is something that we love in matroid theory. Every matroid has its dual, and it basically represents the relationship between row spaces and null spaces. Okay? And so what I'm noticing here is that basically lambda over S needs to be in this space. Okay? And so if I identify C to the R, which is where I was mapping from with V, okay, which is given by these equations, what I get is that S is a critical point of lambda if and only if lambda over S, where I mean like coordinate-wise, is in purple. Okay, which I don't know about you, I think this is really cool. So then what happens then? Basically, we're trying to gather all these points at once, and so what we're going to do is consider all the pairs U comma lambda such that U is a critical point of phi lambda. Okay. And then let me take the closure of this thing. And again, I put U in M because U is in the hyperplane arrangement complement. But I actually want to think of that complement as living inside here. As I was saying, I want to identify M with the torus C star R, and so really I can think of this as living in here. And I want to consider the closure of this. And again, because this is all compatible with scaling, I can do this projectively. Okay, and so this is the definition of the variety of critical points, and the theorem, which I'm kind of sketching a proof for here, is that this is the closure of the projectivization of V times the projectivization of V perp in Pn minus 1 times Pn minus 1, because the first coordinate needs to be in V and the second one in B perp, except that there's this weird twist, right? Because it's not that lambda belongs in PV, it's actually that lambda over S belongs in PV, and so I need to do this strange twist where xy maps to x comma xy, so that when I divide this by this, it lands in PV. So this is a strange twist that happens, and it's pretty essential. But so this is my variety of critical points, and I could have just given you this definition, and sometimes people do that, but I wanted to say a little bit about where it comes from and contextualize to what this has to do with these maximum likelihood degrees, okay? And again, now I do the same kind of thing where this is a subvariety of Pn minus 1 times Pn minus 1, so I can consider its cohomology class. And what I get is now the sum of the HIs where these are the coefficients of the characteristic polynomial like q plus 1, and therefore this is log concave and unimortal. Okay. So that's and this was Juni Ha's proof of this conjecture for the realizable case. And if any of you have looked at this paper that June and Graham and I wrote, it's devoted to studying this conormal fan. And just the one word I'll say about that is that the conormal fan, again, it's just it looks simple because it's just the product of a vector space and its dual. So the conormal fan is the product of the Bergman fan and the dual Bergman fan. But this weird twist makes us work really hard, and it's an important twist. Okay. I'm realizing I have 5 minutes left, so I wonder if I should. I could tell you a word about A, or I could just stop and take questions.
I don't know. Do you want to spend 2 of your remaining minutes talking about A? Or
Sure.
is that reasonable?
Yeah, let's do that. Okay, so A is similar but different because actually these things are not log concave, and so you somehow need to work somewhere different. So A, at least in the realizable case, well, it's inspired by this construction that I did with Adam Booker that I'll talk a little bit about. So here, what we do is we take our vector space in Cn. So I take this vector space, okay, and then we just say, okay, well, we can always compactify C and make it be like, C sort of P1. Okay, and we can say, okay, so when we consider V inside Cn and then Cn inside a product of n projective lines, what happens when we take the closure of V here? So this is this object that we constructed with Adam, and we found that it has a very beautiful Grosvenor geometry and very nice combinatorial properties. These days people are calling this the Schubert variety of the matroid. So if you hear that, it's this thing. What happens here is that okay, and here again, part of my being given an honest talk is to talk about where I start getting where my technical knowledge falls short. So for reasons that I don't fully understand, you have to. They work with étale cohomology here, so you could do various cohomologies, but so you could consider Chow cohomology, étale cohomology. But basically, you want to understand the cohomology of this thing, and it's very nice. So it's a direct sum of over flats. Where the product of these things, okay, and a flat is one of the intersections that I had there, right? So either the hyperplanes or the lines or any intersection of the hyperplanes, and this is either the join of the flats or 0 according to some rank condition. So if it's like full rank, you get this, and if it's not full rank, you get this. Okay, so this is graded. And then what ends up happening is that the dimension of the ith piece, by the way, this relies on some work of Bjorner and Ekedal, so I think they're the ones who realized that étale cohomology of these things also had nice combinatorial properties. But the point is that if you look at the dimension of the ith piece of this, then you end up with the number of flats of rank I. And these are the things that we're trying to prove have these nice properties. And this is exactly the kind of thing that the Hard-Lefschetz theorem does for you. So Hard-Lefschetz gives you inclusions from B1 to B2 up to half. And if you have inclusions, that means that these inequalities hold. And it also gives you an inclusion from Bi to be R minus I, multiplying by some Lefschetz element by high enough power, by the correct power. And so that gives you these inequalities that are theorems now, okay? And again, there's a I'm not an expert in how Chow cohomology, étale cohomology, intersection cohomology are all, like which is which, what properties they have, and you end up relying on the fact that intersection cohomology uses the Hard-Lefschetz theorem, and it plays nicely with étale cohomology to get these results. So there's kind of a geometric part here, and there's a nice combinatorial algebraic analysis that you need to do to get there. So that's kind of a brief overview of this story. Like I said, each one of these things now has a parallel story for any matroid, and that's a story that I would love to talk to anybody about who wants to talk about it. But I think that's a good place to stop.
Questions?
I'll ask a question.
So what's the relationship between the tropicalization of this X bar and what you call the co-normal fan? This X bar, the closure in this product, fancy X bar.
This one.
If I tropicalize this, then I can study your co-normal fan. Are they the same? Are they related?
They're the same, yeah. They're the same. Although there's some technicalities to show why they're exactly the same, but yeah.
It's so clear, doesn't it? No question.
So I was wondering if I plug in some random values for lambda, I want to count the number of critical points, and that should can I see from this formula for the cohomology class that that's the number of bounded cells in the arrangements?
The short answer is yes, and I mean, all of this is kind of motivated by Barchenko's result of the number of critical points is some Euler characteristic under some hypothesis, and this is a stronger statement than that, and I am pretty sure that it should follow, but maybe we can talk about exactly how it follows. But this is kind of generalizing that story. Yeah.
So the assumption is that you have a hyperplane arrangement. Does this have an interpretation? Is there something for hypersurfaces? So not just polynomials instead for the Fs? I'm sorry.
I think this is a great question for Bernd. I mean, so this is we can consider this master function, and I consider the master function of those linear functions f1 up to f5, but you could consider it for any polynomials. And so, I mean, there is this whole story
That's
of
what we need in physics.
okay. And I mean this conormal variety that I studied that I talked about, we care about it in this case, but it's defined for any polynomials.
We call it the likelihood correspondence. So it's for any model.
But I would love to hear about how you need it and what you need. Yeah. I mean, I think with all these things, like there's a general theory, and when you want to apply to a specific case, then you need to do some combinatorics to get it to work usually.
I
So,
wondered
yeah.
what among the technology with X, fancy X, would if there would be some analog there.
If there's no other questions, let's thank Federico again.